Alright, I don't have a lot of time to make this video, so let's start right into this. This is an example of an elastic collision problem. Now I know a lot of things are kind of jammed in here because I don't have a lot of space, but this is a type of elastic collision problem, and oh my gosh, I have the answer up here. I don't know if it's the answer, but anyways, we'll find out. It doesn't matter because hopefully this is practice anyways. Alright, so what we have here is a system. There are two objects, a 10 kilogram object and a 2 kilogram object. And we're going to assume that this is a perfectly elastic collision. Now, in an elastic collision, they bounce off each other, so there's no energy lost. The momentum will be conserved, and there's no energy lost here in this system. If we want to figure out how fast this object's moving after the collision, we simply have to use the conservation of momentum to figure this out. Because although we don't know what the total momentum in this state should be, we do know what the total momentum in this state is. I mean, we will figure it out. We can just calculate it. Once we have the total momentum here after the collision, the total momentum must remain the same. And so we can figure out the total momentum on this side, and it'll be the total momentum on this one. So let's go ahead and start that. Now you're going to see that I'm going to write out stuff maybe a little bit differently than you would, but I would really advocate trying it out. Also, again, make sure that you're well, I'll tell you in a minute. I want you to actually try to solve this, but all right, the total momentum. So we know that momentum, and if there's one thing you remembered in this unit, you need to just have ingrained. I usually say don't memorize an equation, but you need to memorize this one, P equals mv, because you use it so often. It's so simple, and you just need to have it memorized. So the total momentum is essentially going to be, let's label these two objects. And again, you can label them yourself. Sometimes they will be labeled, but you can always add your own labels. So the total momentum is going to be the momentum of A, which I'll just say is PA, plus the momentum of B. That is the total momentum. Now we just need to figure out what PA and PB are. Now, again, we have this equation P equals mv. So the total momentum could be written as, instead of PA, let's actually write what that is. Well, it's the mass times velocity. So we could write MAVA, right? A is mass times A velocity, plus MBVB. This is the exact same thing. This is just a bit more descriptive, a bit more helpful, honestly, because we might not know some parts later. So now plug in everything that we can. So this is where I would encourage you to pause the video, plug in everything you know, make sure that you know how to get the total momentum, because there is something in particular about the velocities in case you forgot. So go ahead and pause here and calculate that total momentum. Okay, hopefully you paused. Here's what we have. Again, the mass of A is 10 kilograms times the velocity of A is 0.5. Now since that's going to the right, I'm going to assume that's positive, plus the mass of B times the velocity of B. Now here again, this is a velocity, so I'm going to put -8 since it's going in the opposite direction. It's going to the left. So now we are going to need to calculate this. So 10 times 1/2, I don't have my calculator, hopefully I can do this right. 10 times 1/2 is 5, plus 2 times -8 is -16. Alright, so we have 5 plus -16. Well, 5 minus 16 is the same thing. You get -11 kilogram meter per second. Alright, this is the total momentum, so very important. You understand that you can even put it up here at the top because it's going to be true. The total momentum is going to be -11. Alright, now let's write this exact same equation for the second half, for this side. Okay, so I hope you understand this dotted line is like this is before the collision, here's after. So let's talk about after the collision. Well, let me put my units on there. Alright, let's talk about after the collision now. I'll just do it in different colors so it stands out a little bit. Again, we still have A and B. We know A's velocity, we know A's mass, we know B's mass, but we don't know B's velocity. We're not sure how fast it's moving. So we need to use what we know, the total momentum, to figure out what this velocity is going to be. So let's start by writing the equation for total momentum on this side. And if you will allow me, I'm going to make a shortcut. I'm basically just going to start here. So we have MAVA plus MBVB. Alright, so when I plug everything in again, I would encourage you here to pause, try to plug everything in. You know. So here you've got the mass is obviously 10, but now the velocity is going left, so it actually has negative velocity this time. Plus mBVB, that's 2 kilograms is the mass, times, we don't know its velocity. Now you might assume it's positive, but we actually don't know that it is. Maybe it won't be, I don't know. I think I might have messed up on my calculation. So we actually don't know the velocity, so this arrow maybe shouldn't even be there. We don't know. Let's figure out how fast it's going to go though. So we know its velocity is x, or I'll just leave it as VB for now. Or VB, because I don't know what it is, so why not just leave it? Alright, so if I simplify a little bit, P total is going to be 10 times negative 1 is negative 10 plus 2 VB. Alright, so now we need to figure out VB, but we have to plug in the total momentum. So here's where that concept of the conservation of momentum comes into play. If we know that the total momentum before was negative 11, that means it still has to be negative 11. So the total momentum just negative 11 kilogram meter per second. Ooh, and I was right. I think it is going to be negative. So see, this is why you don't know which way it's going to go. And this is fun. Alright, so you're just going to solve for VB at this point. So I'll add 10 to both sides. I get negative 1 equals 2 VB. And then when I get VB by itself, I'm really running out of space, I apologize. To get VB by itself, I divide by 2. And so I get VB equals negative 1 divided by 2 is just negative 1/2 meter per second. So that's how fast it's going. So it's actually, it turns out that this thing is actually still going. And see, this is why I got to flip this around. It's actually still going this way. Now it's not going as fast, so this one will get out ahead because this one's only going 1/2, but this one's going 1. So again, this is the example of the total momentum of a system. And it's really important. I know a lot of you could like sit here and be like, well, I don't need 5 plus negative 16, and that's good, but I'm telling you, later on, if you don't get used to the symbology, yeah, I think that's the word, symbology, you're not going to be like as familiar, because right now everything is nice and one-dimensional, right? Everything's either left or right, positive or negative, but we're moving towards a place where it's going to be two-dimensional. It's going to go in 2 directions at once. So I think that's all for this video. Hopefully that made sense.